Great, thanks so much, and welcome everyone. I hope you all are doing well and you're staying safe. Happy to have you on for today's webinar on battery storage, part of our series on innovative technologies. My name is Craig Haglund. I'm with the EPA's Energy Star Buildings Program. I lead our work with commercial real estate and multifamily sectors. So before I get going to introduce our speakers, I wanted to give a little bit of a primer, I guess, rudimentary primer on battery storage. Battery storage, sort of simply, gives the ability to take energy being produced at one time and allows it to be utilized at a different time. In the utility setting, taking into account generation curves, typically this is storing it from the off-peak time, which is usually in the middle of the night, and then utilizing it during the peak hours, which is typically in the afternoon when everyone's at work and out the setting. This helps to flatten the demand curve, which is beneficial to the grid and utility, and leads to more stability there, and utilities don't need to ramp up additional power plants to meet that peak demand. But on the customer side, in this case, commercial real estate, one of the benefits is avoiding energy during the peak hours, and thus avoiding additional costs that come with energy demand charges, which commercial real estate certainly knows a lot about. Typically, at a given time where you have peak demand charge, this could be anywhere from 30 to 70% of an electric bill. In 2017, there was a study published by the National Renewable Energy Laboratory as well as the Clean Energy Group that found out that about 25% of all commercial customers in the U.S. could cost-effectively reduce their electric bills through on-site battery storage and addressing these demand charges. I would be remiss if I didn't mention one element of Energy Star Portfolio Manager that we updated a couple years ago and gave the ability for a user to track energy demand as well as energy demand charges. The idea, as with all of the metrics on Portfolio Manager, to give some visibility into how this is affecting your properties and portfolios. That gives a view into that, and battery storage certainly is a way of attempting to address that directly. So without further ado, I will introduce our speakers today. First, we have Gary Peterson, who's a Senior Engineering Manager with Hines. Gary's been involved with all different aspects of building startup operations, maintenance, and assessment, and has been with Hines for 25 years. Sarah Neff, next, is Senior VP of Sustainability at Kilroy Realty. She oversees all these sustainability initiatives, including solar and battery deal making, as well as the implementation of energy and water efficiency initiatives. All right, and I will pass it over to Gary to take it away.
Thank you, Craig. Yeah, so welcome everyone. A little bit of introduction here about our project here in Hines. I mean, Hines is a large property development manager operator operating in over 205 cities in 24 countries worldwide. We currently have about 4,500 employees throughout the globe. I'd be remiss if I didn't mention that our founder, Gerald Hines, passed away, unfortunately, last month at the age of 85. But really, the direction our company's been going and will continue to go is really his vision, which continues today with his son, Jeff Hines, running the company, and his granddaughter, who is also taking the lead in this within the Hines company. So move on. The project we're talking about today is really the 101 California Energy Storage Project. 101 Cal is a 1.25 million square foot office building in the central office area of San Francisco. It built close to 40 years ago, 1982. We have a peak demand in our building here of about 3 megawatts. We installed our energy storage here back in 2018, but the process really started in about 2015 when we started really trying to evaluate why it might be a good fit for our building here. And we worked with STEM, who is a provider of these systems, and we were fortunate enough that they're just down the road from us in Millbrae. So we were able to work really closely with them through the process to kind of figure out if it was a good fit or not. So YES, our energy storage systems. Clearly, number one was, this was our original thought, was try to reduce our energy demand costs. And you'll see in a little while what that means in California. But our costs are significant here in California for our, not just energy use, but also for our demand costs. The other component of that was really, at that time, again, we're talking 5 years ago, we were really looking at ramping up our EV charging operations, and we thought this might be a good fit for offsetting some of those charges. But as you'll see later, that kind of vetted itself out as not really being a good assumption. So give you an idea, San Francisco, PG&E, Northern California, our average cost per kWh this time of year, we're looking at about 25 cents a kilowatt hour average cost per kilowatt. Our demand charges, at this time of year are above $45 a kilowatt. So you can see where you'd think that, with the battery storage, we could have some significant savings by adding a battery storage to reduce that. And, we'll see that our demand charges are really about 50% of our total energy spend this time of year. So, kind of getting back to the EV charging, so I think this is a really big component of some of the challenges that we're facing from an operating building. Here in San Francisco, San Francisco has an ordinance in the works that by 2022 that we will be required to have 20% of our parking stalls have battery storage. So as you can see, that we're talking about a 200 kW demand, potential demand, by just having having EV charging within the building. And this time of year, that would equate to about a $9,000 charge to that operation. So some installation challenges, and I'm talking really about specifically the 101 project here. San Francisco, the way our downtown infrastructure is designed, we do not have the ability to export power. So if we do produce any sort of renewables, we have to use them on site. We can't export and import as our capacity actually increases. So that was certainly a big hurdle for us in trying to figure out how much capacity we could actually install here that we would be able to use pretty much 24/7 and never have an export situation. One of the other challenges was our metering scenario here. As you'll see kind of in that picture there, we have six main switchboards, each about 2,500 kW each, that all aggregate up into one number. And that's really our demand for the building and what we're billed at. So basically 6 switchboards. We had to pick one that would allow us to install a battery storage, figure out where we could tie that in, and be able to use any energy that may produce at any given time. Other challenges was certainly footprint. The system that we put in here, if you look at the footprint that was required, it was really about 15 feet long by about 6 feet wide. So pretty significant, footprint really for what we're trying to do, especially in an operating building where we've already kind of capitalized on any, holes and maybe nuggets where we could have installed something like this. Weight was certainly an issue. Wasn't something we wanted to put up on a roof. You have to have that additional expensive structural reinforcement and all. The other one was where to plug it in. Again, that kind of goes back to what I was talking about, the metering and having to find a switchboard and a place that we could actually plug this unit into the infrastructure. So, kind of the economics, the way our program worked at least was, STEM came to us with a proposal. There were no capital costs from an ownership standpoint for this. All of it was going to be paid through the incentive programs and through STEM. So that was pretty seamless. We basically a monthly fee, almost like a subscription to the system. And then the contract actually allows us to do a true-up every year just to make sure that, we're not actually losing any money. And that was really put into place because when we started this whole process, it was all pretty new. It was, kind of a new thing, and seeing if this was actually going to be a viable thing in some of these large high-rise buildings. So we wanted some reassurances that we would not actually have a negative cost to our tenant base. And as you can see, there were some hiccups just on that installed cost. The original estimates were about 35 grand to put a 100 kW battery storage unit. Actual cost came in about 90,000. A lot of that was due to just a lot of the metering requirements that were required, the tying into the existing infrastructure, and just the cost of labor that really drove those costs up. So that was kind of a hiccup, but we were able to figure out how to make it work. The money comes from here in California. We have the self-generation incentive program, which encompasses, the solar, any energy efficiency programs, and battery storage is kind of another component of it. So that was really what made this as a viable project to continue with at this point. Just a quick picture of what the units look like. And you'll see one of the things that's kind of interesting about them, there's really not a lot to look at when we look at these battery storage units. It's basically just towers of batteries. In this installation, we had 4 towers. Each of them had its own switch gear up on the top of the units. Lithium-ion batteries that fit into racks, and they're, the STEM system is really battery agnostic. So this system is a Samsung system, battery rack, but really the type batteries they use or the manufacturer really isn't that important. It's really about the capacity of those batteries. And then to the right of this, you'll see the inverter, and that's what actually does the work of getting the battery juice back into the system and then actually charging up the batteries as they're depleted. So how do we save money with this thing? I mean, there's really two things that we're trying to do with it. One is the demand charge management, and that's really trying to shave off that peak demand in the building, and then energy arbitrage. And that's something that really is kind of new that we're doing, and I'll explain that a little bit more as we go through, but it has helped with the economics of this project. So within the STEM system, they have a program called PowerScope, and that's what's actually our interface into the system. Athena is their kind of AI that is doing the work in the background, but I thought it would be kind of interesting to just kind of show what we're trying to do here. You'll see in the middle of the screen there where it says the demand is 3.04, and that resets monthly. If you think about it, that's kind of like the ceiling, and it's kind of the game of, okay, we got to stay below that number, and every point that we can stay down below, we save $45. We save that demand on that. So if you look at this graph here, you'll see the green is our building demand, and you'll see the little peak up there that I put in as demand relief. And that's where our batteries are actually discharging and trying to maintain that peak and keep it below that. It's actually looking at the building load every 10 seconds to determine, okay, is it going up? Is it going down? Do I need to put on some batteries to keep that 15-minute load below that? So that's kind of the way it works. It was, I always thought it was you turn on the batteries, you depleted them, and then you charged them at night. And that always sounded pretty viable reason why to do that. But if you look to the kind of the right, you'll see a line underneath the green graph, and that's actually batteries charging. So the batteries are kind of charging and discharging all day long. Just the key is just really to try to keep the peak down below that 3 megawatts. So if it drops off, it's going to try to charge them to give it the capacity if it needs to do some more discharge later on. Energy arbitrage. So this is the good old, sell high, buy low, right? So what we do with the battery storage, if there's any energy that's left when we're getting towards the end of our peak period, is we'll actually discharge the batteries. 6 p.m. is when our peak period here goes off. So you'll see about 5 o'clock we energized the batteries, dropped our demand off, and we saved some of our kilowatt hour costs. If you up at the top there, you'll see, the peak period we're paying over 16 cents a kilowatt hour. So the net is about 7 cents, and so we discharge the batteries and let them stay discharged till about 10 o'clock at night when we go into our off-peak hours and charge them back up and we buy the energy back. So it's kind of the vicious cycle, right? As far as efficiency on these units, I'm told that they're about 85% efficient. So you get about 85% of the energy that you put in them out of them. So a little bit of inefficiency, but it seems to work. Again, here's a typical day. Again, this is kind of post-COVID, so our demand's down a little bit. But you'll see where earlier in the day we're discharging our batteries using that energy for demand relief, and then about 5 p.m. we actually had a little bit of energy left, and so we discharged the batteries to save a little money on the kWh costs. And then 10 o'clock at night we charge them back up and get ready for another cycle. So economics, when we went into this project, we had a annual cost. That's kind of our subscription cost to STEM. It's about $8 grand a year, and the projected savings was about $25,000 in savings. What we're actually realizing is about $10,000. So it didn't really play out where we thought it was going to. And again, I think the big key is, it was really a learning experience both for us and how these systems work, and for STEM also to determine if this is really a viable market for these type units. So why the big discrepancy? And really what we found is, our office buildings, we really have a pretty flat load profile, at least in this market here, where we start up, power comes on, we run for the day. We don't really have any real spikes in our demand. So it really ends up with a thing, okay, if I have a battery, how long will those batteries last? In our case, basically because the load was so flat, we didn't get a lot of kW benefit from it because we couldn't ride it out through long enough with the actual capacity of the batteries. They literally ran out of energy before we really got a lot of benefit. So it was just those little nuggets, and good news is we're still saving some money, and I think again it's been a real learning experience. The one thing that I want to kind of point out, because I kind of made a big deal about the EV charging, and that we thought this was going to be a good solution in helping with that demand that operation is starting to produce. And kind of what we found is not really, because when we plug a car in, that's a fixed load. It's not really varying, and so we have a situation where, again, we just don't have the kilowatt hours with our battery storage to be able to ride through those long duration and provide a benefit. We have seen a lot of other benefits from the system. With the STEM software, we're able to use that data, and having that real-time data available to us, we're able to use that. We have 11 engineers here at 101 California, so for us to be able to look at where our energy going in real time and be able to make better energy decisions as far as how we're operating the building, it has had a lot of benefits for us. And I think that's been probably one of the biggest benefits of the system, is just really having the ability to really get down and look at our energy, where we're using it, when we're using it, and how we might be able to better use that. And I'm going to go back here. I just wanted to add a couple of things. In California, I don't know if you guys have been following this at all, but California, we've had some real challenges lately. We've had the fires here recently. really high temperatures. And, you know, the first time in 10 years, we've actually been experiencing some rolling blackouts here in the San Francisco Bay Area. And, you know, as we've gone forward, California's done a really good job of promoting the solar. I think California's up to somewhere in the neighborhood of 31% dependence on solar energy right now. And that's great when the sun's shining, but these rolling blackouts have typically been happening in the evenings when all that solar production is going offline. And, you know, I think that the battery storage is really going to be necessary for us to be able to ride through these periods when we have these heat spells and everybody's going home and turning on their air conditioners. So should we continue to do it? Absolutely. Is this the market to be able to work in? Maybe. I think there's a lot of smart people out there looking at it and trying to figure out how to make it more viable in this market. But I think it's again, it's kind of the Gerald Hines innovation, not the status quo, and making sure that we are moving forward and trying things to figure out what works and what doesn't. That I'll pass it on to Sarah.
Thank you very much. I'm waiting for
it should be coming.
The ball to come to me.
All right, Sarah, you should have the ball now.
Yep, looks like I have the ball. And as is the case with COVID, I'm having a very minor family issue, and I will be back. And I'm back. Thank you. So sorry about that. It is life during COVID. Hi, my name is Sarah Neff, Senior Vice President of Sustainability for Kilroy Realty Corporation, and I'm going to talk about our battery projects. So here is our story. Okay. Come on. For some reason, I'm very moving back out. Okay, there we go. So this is me at the ribbon cutting day for our battery storage project in Long Beach. Kilroy now has 9 battery storage projects located across a few campuses, all in Southern California. We actually had 4 battery projects that we were supposed to do in San Francisco, and the story with Hines is incredibly interesting given the context of what happened to us there, which I will get to in a second. So just want to talk about our battery portfolio overall. 9 batteries with 2 different providers originally. So we had batteries with AMS, Advanced Microgrid Systems, who did a basically did a portfolio-wide survey for us, chose which sites they thought would be most attractive for batteries, and installed batteries there. They then didn't want the rest of my portfolio, and then STEM, who Hines worked with for their project, came in, said, we have a slightly smaller solution. I think we can make something work, and then chose additional sites in our portfolio, which is how we ended up with 2 providers. And our total installed PW capacity is slightly over 4 megawatts. So I'm going to get into a little more details of what we did. So I want to just put this into context. As Gary mentioned and Craig as well, battery storage is sort of the next in line of a lot of things the building owners like Kilroy and like Hines have done to try to modulate energy use in our buildings, specifically around trying to save on energy bills related to peak demand. So load shifting, something we still do, for example, pre-cooling in the night so we don't have to run the cooling system during the most expensive part of the day. Peak shaving, turning off systems at the like lighting and other non-emergency uses of power during the day, trying to get people to unplug their laptops, that kind of thing. These days we use automated demand response for almost all of that, and ADR, automated demand response, is still a part of our sustainability footprint. However, it does have its drawbacks. It's quite hard to reduce meaningful energy load on the days utilities need it most, such as the hottest days of the year, which you've heard about from Gary. And so we definitely were looking for other options to reduce peak demand on those days. So Kilauea had been doing, in some ways, storage for a long time. We actually had thermal storage, which is what the ice is supposed to say because it's an ice plant, installed on a couple of campuses back in the early 80s. And that had worked really, really well to reduce peak demand. Obviously, we've been installing electric vehicle charging stations for a long time, and that's helping with cars and storing their batteries and all that. But then we really felt like the next phase for us was going to be on-site battery storage. And why? Why did we do that? So I'm going to talk a little bit about why we did the deal and what the economics are. One is it's good for grid resilience. You heard that from Greg, you heard it from Gary. We are, our grid is very strained, and especially these days where, we're getting all sorts of alerts, please don't, run your power during these hours of the day or those hours of the day because, with heat, and that's not an issue that's going to be going away anytime soon, the grid is strained as people are trying to cool their buildings on the hottest days. And anytime we can take load off the grid during those days, it's good for the reliability of the grid to avoid things like rolling blackouts and brownouts. The other reason, second reason that it's good is it's great environmentally. Yes, we have some issues with what happens to battery disposal at the end, which very smart people are working on. But what utilities do otherwise when they can't meet peak power is they have to, turn on or even commission new peaker plants. These are natural gas plants. They are not particularly clean, and it's not the cleanest way to run the grid. The grid gets dirtier if peaker plants have to run. So the right thing to do for the grid is ideally be able to not have to turn those facilities on whatsoever, and you do that in many ways through battery storage. The other thing is this made sense financially. So we had a different deal than the one that Gary described, which I think will be interesting to people on the call. So with both AMS and with STEM, we, instead of taking the operational savings for the battery, we decided to take a rent payment. So very similar structure in the sense that we didn't pay an upfront cost for the project. That was paid for by the developer, and we so that there's no upfront cost, and all of that SGIP, the self-generation incentive program, all of those benefits we signed over to the developer for that. In exchange, we signed a lease agreement, so not just a traditional battery agreement. We signed one of those, and we signed a lease agreement, and we did that so that the batteries themselves could act like tenants in our buildings and pay us rent. So the rent is on average about $22 a kW for an overall increase to our rental income for the company across the 9 sites of just under $100,000 a year. So it's fun to sort of make up rentable square footage from thin air, which is how I certainly felt like it about it. So it was fun. It's not, these are not enormous numbers across 9 sites, but it is meaningful numbers, especially if you can get it to scale. In exchange for giving us rent, we do not experience any operational savings from our batteries. So the batteries do save the building money, but we just pay that exactly back in a maintenance fee. And so we basically decided to turn the operational savings into a rental payment. It works better for us as a REIT and other reasons that I can go into. So that is how our battery deal is structured. I want to talk a little bit about how to do these projects. We're going to get into incentives later, but really, really important to pay attention to incentives. Batteries are currently a new enough technology that they only usually make financial sense if the right incentives are in place. So once you figure out if your geographic region is viable for battery-based incentives, then you analyze your portfolio to see if you have enough load to be able to justify a battery, not just load, but also a location to put it in, and I'll get into that in a second. And an RFP goes out, proposals come back, pick a winner, contracting, which is not a particularly fun process. We spent a lot in contract negotiations, which I'll get into. Then there might be accounting issues, which we went through as a real estate investment trust. What is this income? Is this okay? Is this considered typical? Dealing with that, and then construction and interconnection. So these are the basic steps of how our battery projects came together. So now we're going to talk about the challenges we faced. One was those incentives. These are can be fleeting. So, for example, our first batteries, the SCHIP incentives were pretty robust back then. And so we were able to get much better rent than we were on our second round of battery projects, even accounting for KW. But the incentives come and go. And my recommendation is always to lock in incentives as soon as you possibly can. They tend to not particularly get better. And then you can ask for delays, and, you know, when your interconnection dates are supposed to be, far better to ask for delays and lock in really good incentives than to wait and to then end up with a deal that's underwater because the incentives didn't materialize. So it's very much something to monitor is what the incentive situation is where you are considering a battery installation. Next thing is negotiations. Look, anything related to energy is no particular fun to negotiate. We have, you know, close to 6 megawatts across 12 sites of solar in my portfolio, 2 different battery contracts. I'm not unfamiliar with negotiations, but they are difficult. The difficulty in these negotiations, a lot have to do with, the idea that the battery could be damaging the building in some way, that the battery could be negatively impacting the building. I'll get to that in a second. As well as issues with when you want to sell the building. So what building owners don't want is what's called deal friction, where we want to be able to transact the building and the battery provider just has to deal with whoever the new owner is. This was a major issue. Obviously, insurance is no fun. We'll get into that in a second. And then, you know, issues of who's paying who, delay damages, and access to the site. So these are not easy contracts to negotiate. The next is insurance. So one of the unpleasant surprises we had in this process was sort of external factors causing issues with our battery installation. So for example, we had 4 small battery installations in high-rises in San Francisco, fully contracted for press releases out. We were excited about them. And then the sort of San Francisco Fire Department had changed the rules. So we knew that the change was coming. We tried to quickly pull permits and get them grandfathered in, but it didn't work. And we actually had to cancel every single one of those San Francisco projects because the changes that would have been required for the installation made them non-financially viable. Similarly, we had an issue with installation we had in Irvine because not our batteries, but there have been what I'll call battery combustion events known to have happened in Korea, but there have been some stateside, I believe, in Arizona. And our insurance provider told us in the middle of construction that we had to put in all of this extra protection around smoke detection, thermal, you know, detection, all that stuff to be able to know if the battery was having an issue. And that really wrecked the first 5 years of the economics of that deal, having to put all of that extra stuff in the middle. My recommendation would be to, if you have the space, put your battery as far away from your building as possible so that these issues don't come. So again, there was no combustion issues, and our batteries have been fine in my building. But because there's some concern about batteries from other parties, that was certainly a challenge that was an unexpected issue during construction. The next thing, just a small challenge just to know, is that when you're installing a battery, you do have to shut down the entire building. It can seem, given the amount of rent you're getting, not to be something that's worthwhile. It's something you have to work with the building teams and tell everybody very much up front that this is going to happen. Typically happens at about midnight on a Friday, and it's about 8 hours of work. The building should be back up and running for anybody who comes in on a Saturday. But it is something just to know that this is something that has to happen in order to interconnect the battery to the grid. Also important to note is that these are not currently set up to be resilience tools. That if the grid goes down, my batteries go down too. It is possible to wire a battery to sort of act as a backup generator, but the economics of doing that made the battery itself non-viable. Then we had the experience just this past year of having AMS exit the battery business. And so the operator of most of our batteries was no longer there anymore. That was okay. STEM took actually over those batteries, so then we had integration in our 2 providers, which has made our batteries sort of a one-stop shop. But that was definitely difficult, you know, fixing all the billing and invoicing issues and what was happening. And so, you know, it's still a new market. You know, providers can come and go. And so just making sure that there are provisions in your contract for what happens if one of you goes dark is an important thing to note. Then our next challenge is battery operations. So one of the things that happened to us, and we're not the only ones, is that the battery itself can set your peak demand. And so, that's exactly the opposite of what a battery is supposed to do. But what can happen is that a battery can fully discharge during a peak demand event. And so the building then has to come back online. So the battery thinks, I did a great job. I have taken the building offline during these peak hours. But what happens is if the battery fully discharges and there's no other charge in the battery, the building will then slam back on during the highest, most expensive part of the day and set peaks. And we have seen that happen. Gary mentioned the importance of truing up operational energy savings. This is important, and we did have to, we have a third party who does this for us. We did have to ask for a reconciliation check to come to us to fix this. Again, we're ironing out the kinks in the technology, but it's delicate in terms of making sure that the battery is actually saving the building money, and it is something I would recommend auditing. But we got through all of that, and we're very, very happy with our batteries. I would highly recommend if you do install batteries to celebrate. What I really liked is one of our providers at our battery pickup brought this, which is a cake. It was a very delicious cake that is in the shape of a battery. I absolutely loved it. Batteries are really fun. We were really happy to have them, and also really good pastry shops can make them. Can make a really great, very realistic-looking cake-shaped battery. So I'm going to talk a little bit about the batteries in our portfolio, and then we'll open it up for questions. So we have two kinds of storage. We have exterior storage, which looks like this. All of our batteries, even though they came from two providers, are Tesla. We did go through a bit where one provider on a campus wanted to have two Tesla batteries and one that was a different kind, I think LG, and I had to push back on that, saying that it was going to look like a battery yard sale, and this is not what Class A office property should look like. The concept that the brand name of the battery would matter was new to the battery providers. So again, they're not real estate folks. This is something to think about. So this is an external exterior battery installation in Long Beach. This is our largest. And then we also have some interior batteries. So this one is very small, 18 kW only in a property we have in Santa Monica. And that is battery storage at Tilray, the process we went through, the economics, and what our portfolio looks like. And with that, I will turn it back over to Craig.
Great. Thanks so much, Sarah. Thank you so much, Gary. At this point, we have some time left, and we've received a lot of questions. We have a large number of attendees on the call. So just give 1 minute to organize that, and we'll proceed to a Q&A. Thanks.